The sun generates 90% of its energy in its core. Every second, 564 million tons of hydrogen are converted to 560 million tons of helium. The remaining 4 million tons radiates away each second as heat and light, like the sunlight we saw streaming through our ceiling a moment ago. The sun will continue to burn itself at this rate for billions of years to come, changing hydrogen to helium. It does this by thermonuclear burning, fusion if you will, a process that literally is the ultimate source of energy in the universe. In the sun's core, subatomic particles are racing about at incredible speeds, creating a sort of atomic pudding. As they rush about, they bump into one another. Sometimes they bump hard enough so they can't pull apart again. They fuse, and some of their mass is changed to energy. Here on Earth, fusion researchers have been trying for 20 years to imitate the sun. The high temperatures in the sun would burn any metal to a hot, scalding gas. Everything we know of will melt by about 6,000 degrees Fahrenheit. So we couldn't possibly put such hot, fast-moving particles into a pot and cook them up. And that's the crux of the fusion problem here on Earth. How to keep a group of hot particles in one place without a pot. The fuel for fusion is in common water, the heavy hydrogen that exists in all the world's oceans. Man, figuratively, lives on an ocean of energy. Here are 2 gallons of water. There's a little less than 1/100th of an ounce of heavy hydrogen in here, costing only a few cents to extract it from the water. Fusion reactions occurring in that quantity of fuel would produce the same heat energy as the combustion of 2 tons of coal, or the burning of 300 gallons of gasoline. 1 pound of fusion fuel would produce 40 million kilowatt hours of electricity, enough electricity for 20,000 people for a year. Fusion researchers are trying to liberate some of the energy that holds the nucleus together. Remember, we're working with charged particles, a group of extremely high temperature particles called a plasma, the 4th state of matter. Let's look at one of the more practical fusion reactions, one that occurs more easily than any other. This white ball represents a deuterium nucleus, a form of hydrogen, the most common element in the universe. This red ball over here represents a nucleus of tritium, another form of hydrogen. When these particles are accelerated to high speeds and collide, they fuse, forming a single, heavier, unstable nucleus, which quickly breaks apart at enormous speed, forming a single neutron particle and a helium nucleus. There is less mass at the end of this reaction than at the beginning. This mass has not been lost. It has been converted into kinetic energy. When a nucleus of deuterium hits a nucleus of tritium, they will fuse to form a single, heavier, unstable nucleus, quickly springing apart with increased energy to form a single neutron and a nucleus of helium. That's one possible fusion reaction. Einstein's formula, E equals mc squared, tells us that mass and energy are equivalent. There's another point to remember here. A small part of the mass of any nucleus is present in the form of energy that binds the parts of the nucleus together. It takes less energy to bind the nucleus formed after a fusion reaction than it did to bind the individual nuclei that collided to create that fusion reaction. Remember, if an atom were the size of this room, its nucleus would be no larger than this grain of sand. Normal atoms can get no closer than about 100 millionth of an inch. This is because their outer electrons would touch. That may not seem like much space, but it does keep the nuclei apart. So we must ionize the atoms. That's another way of saying stripping off their outer electrons. Now the nuclei can approach each other much more closely. There's no protective screen of electrons keeping them apart. The sun uses its enormous gravitational pressures to squeeze the particles extremely close together. But here on Earth, we cannot command such massive forces. We must therefore turn to intense magnetic fields or to high-powered lasers. To overcome the mutual repulsion of subatomic particles, we must accelerate them to enormous speeds. This means heat. We must heat the particles hotter and hotter, get them to move faster and faster. If we can get them close enough together, the nuclear force within the particles will take over and they will fuse. Making a plasma is easy. Every time we turn on a fluorescent light, we make a plasma. But as far as fusion researchers are concerned, these plasmas are too cold. Our laboratory plasmas must approach 100 million degrees centigrade. Fusion is heating and confinement, preventing these hot particles from coming in contact with anything solid. Once a hot plasma touches anything, it cools off. It ceases to be a plasma. The problem is not one of preserving the container, but rather one of preserving the plasma. Here's a group of balls representing charged plasma particles. They are more or less moving at random with no particular direction to their motion. When we apply a magnetic field to these charged particles, their electrical charge forces them to spin or spiral along the lines of magnetic force. The magnetic field has given the particles invisible backbones. The negatively charged particles spiral in one direction. The positively charged particles in the opposite direction. As they travel on their helical paths, the particles will occasionally collide with other particles. When this occurs, the particles scatter or jump from one field line to another, eventually drifting out of the center of the magnetic field to diffuse to the walls of the container. Researchers have used a number of different shapes to confine plasma particles. One of these shapes has been a magnetic mirror. Here's a hollow piece of straight plastic tube. It's wrapped with electrical windings that create the magnetic field. We pump most all of the air out. Then we inject our fuel into the tube, apply an electrical potential and a magnetic field. This field forces the charged particles toward the center of the tube, creating a small diameter plasma about the size of a garden hose. To prevent the particles from escaping out the ends of the container, we place strong magnetic fields here at each end. These strong magnetic fields act as mirrors. As the particles approach the ends, they face a more powerful magnetic field than the one in the middle. This turns them around, and they bounce back toward the other end in a kind of ping-pong fashion. We call these devices mirror machines. Despite all these considerations, some particles do get lost out the ends. Now, we can design a device that has no ends. We can turn the ends of this tube upon themselves to form a circle or donut. We call this shape a torus. And many research bottles are of such shape, including tokamaks. Theoretically, now the particles should race around and around until they hit some other particles and fuse. Well, it's just not that simple. As fusion researchers have painfully discovered, when we turn this straight tube into a torus, you run into yet another problem. We've compressed the magnetic lines of force much closer together on the inside of the torus, making the field much stronger here on the inside wall than on the outside wall here. Since particles always seek the path of least resistance, they will drift across the magnetic fields toward the outside wall and be lost. Man is trying to satisfy an age-old golden rule which Dr. James Tuck of Los Alamos once told us about.
Now, the golden rule, if you want to make fusion power, is this. You have yourself a bottle. It's got some density of particles, n per cc. It's also got some temperature. And it stays in the bottle for some time tall. Now, it turns out that you've spent some work in getting it up to this high temperature to cook up the contents of the bottle. You spent something. Now then, something comes out in the way of thermonuclear burning. What you have to do is to ensure that there's more comes out than you've put in. And there are certain factors you have to put in because this...
In producing fusion conditions, we do have some flexibility. We can hold the plasma at low densities for, say, 1 second. Or we can choose to hold the plasma at higher densities, say 100 times greater, for only 1/100th of a second. We must also heat the plasma to 100 to 150 million degrees. Now, how can we achieve these incredible temperatures? Well, we can use resistance heating to heat the plasma to about 20 million degrees centigrade. This is the same principle that makes the wire in your toaster hot. Then we can compress the plasma into a smaller and smaller volume, heating it to perhaps 50 million degrees centigrade. At these temperatures, the plasma begins to self-heat to 100 to 150 million degrees centigrade. Heating does appear to be a major obstacle, but not insurmountable. 24 years of effort have produced plasmas that have buckled, many that have kinked, others that have fluted, whipping around like a wild snake to eventually hit the walls and quench out. Still, there's no fundamental reason why nuclear fusion is not achievable. Dr. Harold Firth of Princeton University.
When I came into this project almost 20 years ago, there was a tremendous amount of enthusiasm. Everyone was confident of success. And the reason that mood then faltered for about a decade is that this enthusiasm was a kind of ignorant enthusiasm. If you don't know the subject, then being a good, healthy, cheerful, red-blooded scientist, you're naturally enthusiastic. So, after this initial enthusiasm, then came a decade of caution and skepticism, and now, after 20 years, we are back to enthusiasm. The important difference is that the present enthusiasm is based on information.
Among the things that we know for certain are the following. Fusion fuel is an essentially infinite supply and is available to all countries at negligible costs. Fusion will produce no-noxious chemical combustion products, and there will be absolutely no chance of a runaway reaction. And fusion will not involve materials that could be stolen or used for clandestine purposes. Fusion will involve some radioactivity, but in relatively small amounts. And fusion power plants will be able to be sited essentially where we want, possibly even inside of the cities, where their energy can best be used. Finally, our studies show that fusion power costs should be comparable with those that we have today. fusion research and development problems are very complex. We feel that we have a very good understanding of what those problems are, and we are mounting a vigorous and expanding program to solve them. Later this decade, we expect to achieve a major program milestone, the creation of reactor-like conditions in a hydrogen plasma.
At this laboratory, fusion research started some 20 years ago, and it seemed that one's professional life can be equated to the many machines that he had worked on. At the present time, we're rather preoccupied with our latest device, the Princeton Large Torus.
The Princeton machine is a donut-shaped torus called a tokamak. It's a significant step up in size, confining a plasma that's about 3 feet across. To demonstrate fusion, the plasma must reach 100 million degrees. These Princeton researchers hope to raise their plasma temperatures into the 20 to 50 million degree range, push their confinement times up to 1/10 of a second or so. Their biggest job? Keeping the plasma from shifting up or down, from bulging or expanding, not allowing the plasma to hit the walls of the container. The performance of the Princeton machine promises to be a gold mine of information on the tokamak principle. Its success will tell fusion researchers just how big a step they must take toward the design of a large deuterium-tritium burning machine.
Our initial motivation for building ORMAC, the Oak Ridge tokamak, was to find out how the donut-shaped plasma cross-section behaves as it's made fatter and fatter. ORMAC has a cross-section of about 18 inches. We began experiments in 1972, which confirmed our expectation that plasma confinement is indeed better in a larger device. The second phase of our experiments began in 1973, when we started using neutral beams to heat the plasma to higher temperatures. Right now, we have heated the plasma ions to a temperature of about 6 million degrees C, and have confined the plasma for about 1/100th of a second. We hope to increase these numbers. Much of our work at Oak Ridge and other fusion laboratories is aimed at determining scaling laws, so that when we design and build fusion test reactors, we'll have a better idea of plasma behavior in these large systems.
I've been at this game here in Livermore since 1953. That's over 20 years. I've worked on several experiments, including Toy Top, 2X1, 2X2, and now we're on the air with a new machine, 2X2B.
The Livermore machine is the largest, most advanced mirror device in the world. A new heating system has been added, pushing the temperature of the plasma to 40 million degrees. The theory behind the mirror approach is to bounce the plasma particles back and forth many times before they are lost out the ends of the machine. The plasma is now being held for about 1/1000th of a second, still too short a time. The plasmas created are also still too thin and too cold. But as larger and larger devices are built, these Livermore researchers believe the energies and confinement times will improve.
Okay, great. Doesn't have much of an integral, but
That's right.
here at Los Alamos, our main approach is pulsed high-density systems. Compared to the tokamaks and mirror machine, our plasma densities are 1,000 times larger, and our confinement times correspondingly 1,000 times smaller.
At Los Alamos, the problems are not ones of temperature and density, but ones of confinement. The philosophy is to quickly shock heat the plasma to fusion temperatures and densities before it becomes lost. Early experiments in straight devices solved many technical problems, but all suffered from the plasma leaking out the ends of the tube. In 1974, researchers turned the device into a torus, eliminating the end losses. Currently, the plasma has been successfully placed on a circle. Efforts are now concerned with stabilizing the plasma, preventing it from jumping off the circle by use of feedback circuits.
We at General Atomic are a little bit different than most people working in tokamaks. Both tokamaks and doublets are toroidal or donut-shaped magnetic bottles.
Dr. Okawa and his colleagues at San Diego are working with a unique non-circular plasma. This kidney-shaped device achieves the same confinement times as other machines, but uses 10 times less magnetic pressure. This is an important cost savings in the design of a fusion power plant. The non-circular concept was proven with earlier experiments in smaller devices. Plans are now underway to construct a still larger machine, the Doublet 3. It will operate at temperatures of 50 million degrees. Since magnets are the major expense of a fusion reactor, the doublet design promises to be the least expensive approach. Man's only successful method of producing fusion did not involve magnetic fields at all. That was the hydrogen bomb. That same principle could be used in a controlled manner, using high-powered lasers. Here's how it works. An ultra-high-powered laser would fire its light beam at a very small pellet dropped into a target chamber. The pellet would be hit from all sides at the same time, its outer layers vaporizing away, the inner core compressed. The core of the pellet would be compressed and heated to fusion densities and temperatures before it could overcome its inertia and expand. Pellet after pellet would be dropped, perhaps 10 a second, each releasing as much energy as about 10 pounds of dynamite. This energy could be used to heat the surrounding fluid hot enough to make steam. The laser fusion reactor would be working like an internal combustion engine, putting along. The mini pellet would be quite small, probably a hollow sphere about the width of a single hair. Here are 1 million such pellets. The challenge is to build a laser powerful enough and to manufacture a cheap, suitable fuel pellet.
Computer studies here at Livermore really gave impetus to laser fusion.
This is the story of a force of nature so powerful it killed over 220,000 people.
December the 25th, Christmas Day, very few people, I suspect, knew what a tsunami was. Unfortunately, now, virtually the entire population of this planet knows what a tsunami is and the horror that can strike from a tsunami.
What made it so powerful?
Like the aftermath of an atomic bomb.
Could it have been predicted?
It's a huge catastrophe, the most widespread devastation that we've seen from a natural disaster for centuries.
Could it happen again? It's now 29 days since the tsunami struck, and the world is still struggling to come to terms with the enormity of the disaster. But how and why did it happen? Using eyewitness testimony and scientific analysis, this film details a minute-by-minute account of the unfolding disaster as it tracks the tsunami on its destructive path across the Indian Ocean. It's the early morning of the 26th of December, 2004. Southeast Asia awakes to the morning after Christmas Day. In Sumatra, fishermen are already on the water. In Sri Lanka, 1,500 people begin their train journey from Colombo to Galle, among them British tourist Shenth Ravindra.
I left my dad and his family in Colombo on Boxing Day because I was going to Hikkaduwa to do some scuba diving around the coral sanctuary. My dad was very keen for me to actually catch the train to Hikkaduwa because of the beautiful scenery that I would encounter on the way down.
In Thailand, Tom Travers and Richard Anthony open up their beachfront restaurant.
I went down, put some laundry in, which we came back, ordered some breakfast through. Yeah, it was just another normal day, basically.
And in Hawaii, scientists at the Pacific.
For centuries, sailors have told incredible tales about a freakish, furious act of nature.
They are enormous, they are terrifying, and they are usually fatal.
An unexplained force that strikes without warning.
Next thing I knew, we were upside down, fighting for our lives.
A real-life nightmare tailor-made for a Hollywood disaster movie.
You'd think when you see the movie Poseidon that this has to be fiction, that this is Hollywood, but it's not.
It's a mysterious power that cannot be predicted, prevented, or outrun. But today, scientists are finally beginning to crack the code of what are called rogue waves. Ocean waves, one of the most powerful forces on Earth. Driven by storms, they can reach terrifying heights.
That wave is a good 15, 20 feet tall. Easy.
And we have all seen this kind of wave. The earthquake-driven tsunami and the panic, death, and absolute devastation it leaves behind. These kinds of waves are well documented, but for centuries, mariners have claimed there is another kind of wave, an even more destructive one. 2, 3, 4 times the size of these. A single wave known as a rogue wave that comes out of nowhere and disappears before it can be documented. Tall enough to dwarf a 10-story building or capsize a 100-foot tall luxury cruise ship. On a soundstage in Hollywood, director Wolfgang Peterson has created a new seafaring disaster movie, Poseidon.
I grew up in Hamburg, in the north of Germany, close to the sea. I was a lot on ships out there, and boy, I mean, I have so much respect for people who handle on a daily basis the sea.
Peterson's fascination with the power of the sea made him the perfect person to turn the best-selling book, The Perfect Storm, into a hit movie. And now, inspired by the disaster classic Poseidon adventure, he's tackling the phenomenon of the rogue wave.
It's out there. It's real. It's a freak thing of nature. And that's so scary because it's a freakish wave, meaning there's no rules for it.
You'd think when you see the movie Poseidon that this has to be fiction, that this is Hollywood, but it's not. We know that rogue waves can build to that size. If you were standing on that deck, if you were on that bridge, it would block out the sky itself. It would block the moon.
Unfortunately, how we know, by word of mouth and bits of wreckage, only contributes to the mystery behind rogue waves. For many years, oceanographers claimed waves reaching 120 feet or higher were virtually impossible. Their mathematical models showing a wave of that magnitude could only occur once in 10,000 years. Now, however, evidence is building that the mathematical models have been wrong.
I'm thrilled that Hollywood is getting its hands on the rogue wave, because here we now have a situation where, thanks to the wonders of digital science, we can actually see what the sailors have been telling about for years in the bars of every port across the world.
December 1942, the Queen Mary, one of the grandest ships in history, has been called into service as a troop carrier during World War II. 15,000 troops were packed on board the ship as she steamed toward England, when suddenly, without warning, she was walloped by a 75-foot wall of water.
Now, the Queen Mary, at her highest peak, she was 90 feet high, or very close to that, and she was thrown over to within 5 degrees of horizontal.
It went all the way over to the side. It was just that much for really going all the way, like in Poseidon, and capsizing. And it just, at the very last second, had a little bit of energy left, so to speak, to come back up and right itself. Imagine that with 15,000 soldiers.
1966. The sleek cruise ship Michelangelo was sailing across the Atlantic towards New York. 900 feet long, ultra-modern, and with state-of-the-art stabilizers, the elite clientele didn't need to worry about spilling their martinis. But something happened out there. Because when the Michelangelo linked into New York Harbor, 3 people were dead, 12 more were injured, and the bow of the ship was a mass of twisted steel. The crew reported they were struck by a single wave, over 80 feet tall.
And it happened in seconds. That is the thing that is the most extraordinary. This is not something that goes on for half an hour. This happens in 15, 20 seconds. A whole lifetime of water hits you with power that it's almost impossible to measure.
December 1978, the pride of the German merchant navy, the supertanker München, confidently steamed through an Atlantic storm. The builder had boasted that the München could not sink, what turned out to be an empty promise.
The München got out a radio message in the middle of the ocean, and 15 seconds later, she was gone.
After the biggest search in shipping history, only a few pieces of wreckage and 1 lifeboat was ever found. And there was no trace of any of the München's 29 crew members.
It was that lifeboat found drifting battered on an empty ocean, which gave investigators the sense that a rogue wave had claimed München.
The lifeboat looked as if it had been sheared off its moorings, as if by a jackhammer, which could only mean that something struck that ship over 60 feet above the sea. A maritime court of inquiry concluded that bad weather caused an unusual event, but declined to name just what that event was. In 2005, the cruise ship Norwegian Dawn was returning to New York from the Bahamas with 2,500 passengers. After a day and night of heavy seas, the turbulent ocean seemed to be calming. But early on the morning of April 16th,
the big wave came and just turned our world upside down.
the 1,000-foot ship was suddenly hit by a jolting, crashing blow from an enormous, unexpected wave.
We heard and felt what seemed to be like artillery fire, something like a massive force against the ship that just shook the whole entire foundation of the ship.
The ship took a horrendous bounce, smacked the water,
People were screaming. I didn't know what it was. I just knew that this is not good.
The captain issued a code Alpha announcing a breach in the ship. Water was pouring into the Norwegian Dawn from above.
We were on the 10th floor, so we were up really high. That's where the wave came, okay? That's where it did the most damage.
For the crest of the wave to smash into the elite 10th deck, it must have been at least 70 feet tall. A rogue wave of tremendous power.
There were steel doors on the front of the staterooms, and the force of that wave was so great that it actually peeled them open. It didn't open like this. They were closed, but peeled back, like you were opening a sardine can or something.
The monster wave hit the ship head-on. 4 people were seriously injured. 62 cabins were destroyed. There was broken glass and mangled, twisted metal everywhere. One couple barely escaped their 10th floor luxury suite.
In my neighbor's stateroom, their plate glass actually broke right in. Okay, so that wave came right in. Luckily, the force of the wave took their mattress and flipped it over. They were underneath the mattress. Otherwise, they would have got sucked right out.
They were just extremely lucky. They should have been dead by my standards.
I just remember sitting there at one point dissecting the situation and trying to pull out the most positive thing I could, and that was that, if nothing else, that we were all going to die as a family.
The Norwegian Dawn and all 2,500 passengers did survive. The modern cruise ship was able to weather the head-on blow, the safest angle to handle the wave. Had the ship been hit broadside, the damage could have been far worse.
This has shown me that water is the greatest force on Earth. You better have a lot of respect for that water, because things like this can and do happen.
Massive, terrifying waves. Their origins unknown. Their existence questioned. Until one courageous sailor captured the first hard evidence of rogue waves. When tall ships set sail during the Age of Discovery, many didn't come back. On average, a ship a day was lost, usually disappearing without a trace. Since then, the design, strength, and durability of ships have improved through technology and experience. Yet as recently as 2005, 2 ships a week went down, often under mysterious circumstances. Rogue waves were rarely credited as the cause, since anecdotal accounts haven't counted as hard evidence. Investigators needed proof, like photographs. But how do you photograph a phenomenon that is sudden, strikes just for a few seconds, and is often fatal? In 1980, it happened. The oil tanker Esso Longdok was steaming through the waters off Durban, South Africa. The sea was choppy, with waves reaching 15 feet at most. First mate Philippe Lejour was standing on the bridge when he saw a wave, nearly 7 times larger than any other, appear seemingly out of nowhere, heading for his ship. Near the moment of impact, Lejour captured the monster on film.
That shot of a rogue wave was one of the first pieces of evidence out there to an unbelieving world that rogue waves did exist, a wave that literally is dwarfing this huge supertanker.
The top of the short mast on the starboard side measured 82 feet above the sea. Based on this height, the rogue wave was estimated to be 100 feet tall.
Now, at last, there was photographic proof. They had to sit up and take notice. Steadily, the reports not only began to come in afresh, but began to become accepted.
The crew of the Longdok survived the crushing blow that hit the ship from stem to stern. But 2 years later, the crew of the oil drilling platform Ocean Ranger was not so lucky. Storms in the North Atlantic are some of the fiercest in the world. The Ocean Ranger, operating off the coast of Newfoundland, Canada, was built to handle even the most extreme conditions. The 35-story tall rig was the largest and most advanced of its kind. Weathering a 40-foot wave was nothing to the Ocean Ranger. On February 14, 1982, a rogue more than twice that size, a rogue nearly 90 feet tall, smashed through the windows of the control room.
When you hit a wall of water, it's like hitting a wall of concrete. That's the force of the ocean.
The rogue wave flooded out vital computer systems. The ballast tanks, which normally stabilized the rig, malfunctioned. The platform was thrown out of balance and capsized. All 84 crewmen were killed. It was the worst death toll on record for a rogue wave disaster.
It's still remembered to this day in Newfoundland. People talk about it all the time. Not only because of the loss of all those lives, but because of the power of a single wave to take this massive and powerful platform and send it down.
Even with so much death and destruction, there was still doubt about the actual size of these waves. Then, in 1995, a massive blow to another oil rig provided the first scientific measurement of a rogue wave. The Dropner drilling platform stood in the North Sea between Norway and Scotland. On New Year's Day, 35-foot waves pounded the rig, rough but not unheard of. Suddenly, a wave nearly 3 times larger took dead aim at the Dropner, bearing down at 45 miles per hour. When the wave hit, a laser mounted on the platform captured the first ever definitive measurement of one of these monsters. The wave topped out at 91 feet.
That kind of empirical scientific evidence was one of the important steps in getting the rest of the world to recognize that rogue waves existed, that they could be this high, and that it wasn't just a sailor superstition or an excuse for bad seamanship.
It was only when the Dropner wave was measured that a captain could say that he encountered a freak wave without being called a drunkard.
Oceanographers were able to analyze the wave patterns before, during, and after the Dropner wave, and the results were startling. This is the wave pattern taken over a typical 20 minutes during the storm. The waves vary in height, but still fall within a comparable range. But this is the pattern surrounding the giant wave. From this data, scientists were finally able to assign a definition to a rogue wave. It is a wave at least twice the size of any other wave in the area. A single startling event, unconnected from other waves in the pattern. A true rogue.
Basically comes out of nowhere. You don't see them coming. And at night, it's even worse.
This answers what a rogue wave is. But the answer to what causes a rogue wave is more of a challenge.
Here it comes. That one.
Using laboratory wave tanks to simulate conditions in the ocean, scientists are learning how rogue waves might be formed.
The rogue wave is, first of all, driven by the wind, but modulated by the current.
When strong currents collide with waves moving in the opposite direction, the wave can suddenly become compressed, thrusting it upward, forming a rogue wave. This may explain why areas of the ocean known for strong currents seem to be breeding grounds for rogue waves. The Gulf Stream is one such current, and it runs right through the infamous area known as the Bermuda Triangle.
There is a possibility, there's a probability even, that many of the losses, the unattributable, unexplainable losses in the Bermuda Triangle come not from the forces of the supernatural, but the force of the ocean to generate rogue waves.
Remember, rogue waves by definition don't play by the rules. And the wave tank shows they can also form when currents and waves travel in the same direction.
One of the things that can lead to really large waves forming on the ocean is when waves with different wavelengths meet, overtake each other.
The energy of the merging waves suddenly combines, becomes focused, thrusting a new wave higher. Rogue waves can also form when normal waves meet obstacles, such as islands.
You have waves propagating towards this island here, and as they get blocked by the island, they split and they have to travel around it.
The waves wrap around the island and come back together on the other side, stronger and more deadly.
If you happen to be right here in this part of the island, you could encounter a rogue wave.
The Agulhas Current off South Africa, where the Atlantic and Indian Oceans meet, is a notorious breeding ground for rogue waves. Here you have strong currents, opposing wave patterns, and also underwater obstacles far beneath on the ocean floor.
As an example, here I have a simulation of what is called a shoal, which is just a hump on the seabed. And let's see what happens when waves propagate over this hump. This is the sort of phenomenon that could explain why in some places, like off the coast of South Africa, where there is a plateau, and there is refraction and diffraction and bending of the waves, so that they converge in certain areas, and it could be creating very big waves in certain places.
And there is another condition under which rogue waves form. It is the most insidious of all monsters. The wave that occurs where there is no island, no undersea shoals or plateaus, no crossing currents, only calm seas, and still a monster wave rises up without warning. A monstrous water mountain, towering 100 feet above you, crashing down with enough force to submerge a luxury liner in a matter of seconds. Difficult to imagine, but photos of storm-generated rogue waves prove these monsters do exist. Now, consider this. The same kind of wave with the same power appearing out of a calm ocean on a cloudless day.
I never really believed in rogue waves before. It was something that we would joke about on the bridge of ships. If somebody would slip over the side or something, we joked that, oh, rogue wave, and that's what happened. But now I've changed my point of view.
Rogue waves happen even in calm seas, and in some cases, they're generated by storms hundreds of miles away, pushed and whipped by huge winds. These waves will build up to incredible height, and then as they move out of the storm, continue on, even across a calm sea, to strike someone out of nowhere.
November 4th, 2000, Point Arguello, California. Just such a swell generated by a distant storm slipped silently through calm Pacific waters toward the research vessel Ballena. The Ballena was built to handle rough seas, and Mark Pickett was a 20-year veteran of NOAA, the National Oceanic and Atmospheric Administration.
It was a flat, calm, beautiful day off the Central California coast, and I certainly would have never expected that I would run into such a large rogue wave, and it would change my life.
The captain's assessment of the wave might have gone down as another tall tale from an inexperienced sailor, but Pickett had impeccable credentials.
I operate research ships for NOAA, and I'm also a scientist. I have a PhD in oceanography, so I also do science for NOAA.
Also on board the 60-foot vessel with Captain Pickett were scientist Dr. Guy Cochran and electronics technician Michael Boyne. The usually turbulent waters were calm. The wind was at 10 knots with only 4-foot swells.
I had both doors to the bridge wide open, and I had just taken off my flotation jacket because it was getting warm. When I looked out the port window, saw a large wave coming our way. And I turned the boat into the wave and punched the throttles. And I absolutely expected that I should be able to punch through this wave or ride over this wave.
But at 20 feet, the rogue wave was 5 times larger than any other wave in the surrounding area. And the speed with which it hit didn't leave any time for maneuvering.
I hit it about a 30-degree angle, and it picked up the bow of the boat, and it flipped and twisted at the same time. In an instant, we were upside down, and the ship filled with water.
Pickett's fellow crew members were below deck, underwater, struggling to get out. The bridge doors were wedged shut by the wave's impact.
I kept trying to push it open, and I, of course, was panicking because I wanted to get out of there and I was running out of breath.
By sheer will, the three men eventually made it out and into a small life raft. But after paddling for nearly an hour with only one oar between them, they agreed their best chance for survival was to swim the short distance to the shore.
The water was cold. We had all our clothes on. We were exhausted from escaping from the overturned vessel and trying to paddle. And once I got to shore, I turned around and looked back out. The two other people that were with me were not making it, and they were in the process of going under and drowning.
There's no more terrible thing in the world, particularly to be the captain, to be the person in charge, to be responsible, to look out there and to see somebody dying, and to know that you have to go. There's an old saying in the Coast Guard, you have to go out, but you don't have to come back.
Captain Pickett did go back out and rescued both drowning men.
So the three of us survived the incident with minor injuries from the loss of the vessel, but no loss of life.
For his heroism, Captain Pickett was decorated with the highest honor from the U.S. Department of Commerce.
The people, especially the mariners who have survived freak waves, are quite traumatized, even many years after the event. They really do have post-traumatic stress disorder. That's how terrifying the experience is.
You think you understand the ocean, you think you have the respect for the ocean, but you never think that something like this will occur and turn your world upside down, nearly kill you, and nearly take away a couple people's lives who were depending on you. And going through that and living that is it's a difficult experience, and it's difficult for me to think back and to go back over it. It's amazing power in the ocean for something just to come out of nowhere and completely destroy a 60-foot boat in a matter of seconds.
After incidents like Mark Pickett's trained observations about the rogue that destroyed his research ship, the scientific community accelerated their efforts. Could similar freak waves explain some of the great unexplained shipwrecks of the past? Could the mythology of the ancient mariners have a basis in the reality of rogue waves?
In the past, you're sailing along a small wooden vessel, and suddenly this massive wall of water comes along, and if you live through the experience, you have to have been filled with a superstitious awe and a fear. What could have created this? This is where the idea of the sea monster comes from. Some creature from the depths, smacking the ocean with its tail, moving in a vast amount of water with the bulk of its monstrous form. This is what made rogue waves in the minds of ancient mariners.
When you start looking for clues through marine history, you find them.
1951, the North Atlantic. Captain Henrik Carlson radioed that his cargo ship, the Flying Enterprise, had been hit by a force he cryptically referred to as a heavy sea. At the time, he did not call it a rogue wave. Carlson didn't want to be written off as just another drunken sailor.
His ship cracked amidships. A crack appeared, as if somebody had taken a meat cleaver and hacked down on the ship, right in the middle of the ship.
Carlson and his crew managed to shore up the ship enough to keep her afloat.
Carlson had the wit to send his men out to start winching the ship with wires closed from one set of bollards to another. And when he got them closed by about 3/4 of an inch, he then stuffed that crack with concrete and had them build a breakwater over it. Amazing.
The ship stayed afloat, but 28 hours later, the Flying Enterprise was hit again by a second rogue wave, believed to be 65 feet high.
The mast snapped, all the radio antennae went. The actual metal plates of the ship cracked. That is an indication of the sheer force. It's like liquid hell breaking loose.
40 crew and 10 passengers were rescued, but Captain Carlson stayed with his ship and maintained radio contact.
There were some terrific mountains of seas there. I don't know if you are in the same one, but it was nothing but seas and water all over the place.
British tugs tried to tow the battered ship 400 miles back to Falmouth, England. But only 37 miles from shore, the Flying Enterprise succumbed to the sea. Captain Carlson jumped from the ship only minutes before it went under. Back home, he was greeted as a hero. His belief that he had been hit by not one, but 2 rogue waves, he kept to himself.
Part of the reason why the rogue wave didn't become respectable for a very long time was because sea captains didn't want to admit to having been overpowered by the weather. They're very proud of their skill, and rightly so. But then it became evident that it was never their fault. All the skill in the world isn't going to save you there.
Captains not only face rogue waves on the oceans, the Great Lakes are another hot spot and the scene of one of the most famous shipwrecks in history. November 10th, 1975, the Edmund Fitzgerald, a freighter carrying supplies for the steel industry, ran into a horrendous storm on Lake Superior.
The Great Lakes of North America literally are an inland sea, and every mariner that sails them knows that. They build up waves that equal anything that you'll find out in the open ocean. So it'd be no surprise then to most to learn that there are rogue waves on the Great Lakes.
At nightfall, the Fitz, as she was known, suddenly ran into trouble. Storm waves knocked out her radar and damaged the ship. Her captain, Ernest McSorley, told a nearby ship, the Arthur Anderson, that he was in trouble, but in control. The Anderson reported back that 2 large waves were heading toward the Fitzgerald's location. Then, in just a matter of minutes, the Fitz disappeared, as did all 29 crew members.
The last contact we had with him, he said, well, he was going along fine and holding his own and no problems. And then when we couldn't see his lights, we figured we should be catching him a little bit because he checked down and then he just wasn't there.
And it is possible, if a rogue wave struck the Fitzgerald, or if 2 struck, that it literally would have torn her in half and sent her to the bottom.
6 months later, the United States Coast Guard found the wreck of the Edmund Fitzgerald at the bottom of Lake Superior. It was split in 2.
The Edmund Fitzgerald was found at 500 feet of water, and she was completely mangled. Now, what kind of force did that? What kind of weight of water? What kind of energy? What kind of massive nuclear force made of water and wind ripped a ship that strong apart so completely?
The Coast Guard was unable to definitively say exactly what sank the ship, but in more recent years, the National Oceanic and Atmospheric Administration has documented rogue waves in the Great Lakes. And in that area off Whitefish Point where she was lost, there you can have the kind of forces that would build up to create a rogue wave.
The re-examination of historical shipwrecks was yielding alarming data. Naval architects studying ship disasters between 1969 and 1994 found that during those 25 years, 60 supercarriers went down due to sudden flooding. On closer study, it was determined that more than 1/3 of the sinkings were probably caused by rogue waves. To try to head off new disasters, scientists needed to figure out the frequency and location of rogue wave strikes. Monitoring the world's oceans was virtually an impossible task until the early 1990s, when the European Space Agency launched Twin Earth Observation Radar satellites, ERS-1 and 2. With satellite technology, international research facilities can precisely pinpoint a particular part of the ocean and map wave activity under any conditions.
This satellite is a radar satellite, therefore it has the capability of imaging the sea surface even at night and through the clouds. So that is very important if you want to see very high waves, you want to be watching the sea surface in storms, and so therefore a radar satellite is the optimum instrument to do that. And then we use these images and translate them into sea surface height, and we investigate the wavelengths, the crest lengths, the steepness of the wave, and the maximum wave height.
The results of the satellite research have been startling, smashing the mathematical model suggesting a 100-foot rogue wave is a once-in-10,000-year event. For example, studying a 12-year period of wave activity in the area of the North Sea where the Dropner oil rig was hit, researchers measured 466 rogues. Then, in 2001, two cruise ships traveling around the Horn of South America, the Caledonian Star and the Bremen, were both struck by rogue waves in one 10-day period. In each hit, the wave smashed into the ship's bridge over 80 feet above the waterline. Scientists analyzed global satellite ocean data for the 3 weeks before, during, and after the Bremen and Caledonian Star incidents.
Within a 3-week period, looking down from space, they plotted 10 rogue waves higher than 75 feet traveling in the world's oceans at the time these two cruise ships were hit.
The largest waves that we found on the images in this 3-week time series were between 90 and 105 feet. The coincidence of the Bremen and the Caledonian Star, that was the turning point for us to believe that freak waves are much more frequent than we anticipated before.
The satellite and radar imaging is being compiled into a wave atlas, a map of rogue wave hotspots, where they formed, how long they lasted, and how far they traveled. In time, the wave atlas will be the foundation of an early warning system, pinpointing areas where new rogue waves may erupt, then routing ships on the safest and fastest route.
If you recognize that you have two different wave systems that will join at a certain point on the sea, then that you can warn for this and say that is an area that is particularly dangerous for rogue waves.
So with the warning from space, we would be able to forecast monster waves within 5 hours or so.
Besides satellite imaging, experiments are being conducted with alternative tracking and prediction systems.
There's also the idea of floating networks, buoys with intelligent computers that have the ability to learn, plot ocean currents, send warnings to each other, and create a neural net, if you will, floating on the sea to send out and broadcast exactly what's going on. That way, with that type of an early warning system, a ship several hundred miles away could be told, a rogue wave is coming your way.
While warning systems get more sophisticated, shipbuilders are also doing their part, designing and building tighter, stronger, more flexible vessels to withstand the force of a rogue wave, if it's even possible. Rogue waves strike without warning, seemingly out of nowhere. That is why the images we have of them are nearly all before and after. What we don't have, with a few rare and grainy exceptions, is what happens during the horrendous crash of a rogue wave disaster. The closest we can come is in the 2006 motion picture Poseidon. What would it look like if a 120-foot rogue wave hit a modern cruise ship broadside? That was the question director Wolfgang Peterson asked the visual effects wizards at ILM, Industrial Light and Magic.
I like ILM for that because they really want to go make it real. Not put some nice effect things together that look great, but this is how it happens. And they study it and they do it in a scientific way, and when they figured it out then they make it spectacular.
The first step for ILM was to build the Poseidon in the computer. The challenge was to make the ship an exact replica structurally, down to the last rivet of a state-of-the-art luxury cruise ship, 1,100 feet long and 20 stories high, with 13 passenger decks. Then, working with a team of wave dynamic experts from Stanford University, ILM created a rogue wave 120 feet tall. Based on real-life satellite data and wave tank studies, the computer-generated wave was so realistic it provides nearly documentary evidence of a rogue wave hit. This was no simple challenge, since realistic water is the most difficult image to create digitally. ILM hired more than 100 software developers, engineers, and artists. They spent over a year developing a completely new kind of visual effects technology so advanced it replicates the patterns of how water moves and breaks apart right down to the molecular level. Then, to recreate the violent crush of water, Peterson and his special effects team decided there's nothing like the real thing.
The entire ballroom was flooded within a few seconds. This was not visual effects. This was 90,000 gallons of water flying through the window.
Rise up over that and just continue on its merry way as if totally unaffected by it.
A 36-foot raging storm wave strikes with the force of about 6 tons per square yard. Most ships can withstand 15 tons without damage. But a 100-foot rogue wave strikes with a force of 100 tons, almost twice the power of an industrial car compactor.
Right now, naval architects build ships to a certain standard. That is, they know the type of stresses a ship's going to undergo in a storm, and they build to meet that and to exceed it in most cases. The question now is, should they build ships to withstand the force of rogue waves?
One of the biggest structural challenges for naval architects is when rogue waves strike high on the bow, smashing through windows on the bridge and upper decks.
Then the windows are hit and then break, and then the electronic gets flooded and the ship can't maneuver.
Redesigning the bridge and its windows to deflect these hits is one solution. The Queen Mary II, launched in 2003, is an example. The $800 million cruise ship was fitted with a thicker forward hull, an enhanced bridge screen, and more pronounced flare of the bow to protect it from large waves. However, these major structural changes still won't be enough if a ship's watertight hatches don't hold.
When a ship hits a big wave and it goes through that wave, we oftentimes call that going submarine. For a moment, you're not on the surface of the water, you're underneath it. You can pop on out again on the other side if you keep your ship watertight. And what's important in keeping it watertight is having every hatch closed. If a hatch fails, the ship's going to start to flood. And when it starts to flood, you lose that buoyancy. The most powerful pumps with enough hatches open to the sea will not counter the effects of flooding, and you'll go down.
To retrofit ships or build new ones to withstand all rogue waves will cost a fortune. Is it worth the cost?
It's an argument that will be renewed every time another vessel is lost to a rogue wave, and it's an argument that would rage just as it does on land after an earthquake, when people say, okay, we've built to this Richter scale, should we now build for the superquake? Maybe the question is not building to encounter, but finding the means with technology to avoid.
Even with its perils, man cannot resist the lure of the sea and will continue to return with incredible tales of the one that got away, the white whale, the giant squid, or the towering, crushing rogue wave.
Felt like a sledgehammer hit the back of the boat, a large sledgehammer.
Literally looked like an alligator mouth. He had a gap from his bow all the way back to
Picked
about
our
an
bow
inch.
up and flipped the stem over stern. Extremely violent, extremely fast.
Tremendous force, the way it slammed down. You thought the ship was breaking apart. You really did.
These massive waves have been called monster waves, they've been called freak waves, they've been...
Places at night I go, places at night. Lights glow, darker inside.
Yes, you locked in, locked on to the Human Traffic Radio Show. Alongside myself, the pressure. Stepping up all the way out of North Germany. Let's go.
I can't breathe. I'm giving this time in lightless streets. I'm bathed in night. The things that fade are only mine. Closer it seems. Don't worry. take it down to the bone.
Yes. All right, okay, all right. Sending a big shout out to each and everyone on the DMV Radio Shed Room. A big shout out to everyone on the Facebook live stream. Yeah, facebook.com/DMV Radio. You can see me there spinning some tunes. Yeah, rolling with some heavy artillery stuff today. Few up front levels. All right. Yeah, I hope everyone is cool. Yeah, hope you're good. Yeah. To scarce for the last hour, out to DB Pro. That's good down. Easy. Let's have it, ladies and gentlemen. Here it comes. back from the music. Yes, yes. Out to my brother. Take rat. Run and rat. Alright, we roll with a wicked job and a wicked roll with a wicked vibe. We roll with a wicked job and a wicked roll with a wicked vibe. We roll with a wicked, we roll with a wicked job and a wicked roll with a wicked vibe. We want to do what was it 7, 8, 9, 10. All I can let them come with the remix again.
by droning bells.
mix.
Don't be afraid.
Well, I don't know where to start.
I feel like a man that's drowning.
Don't be afraid.
Bye.